The motivation for this video was a question regarding the origin of a small peak in magnesium oxide when measured using an aluminium monochromated X-ray source. The answer to this question is that this is a ghost peak. But to understand what I mean by ghost peak, I need to explain how the X-rays generate photoemission lines within an XPS spectrum. An XPS spectrum for magnesium oxide contains a set of peaks that are above a background signal. And these peaks can be described as either photoelectron peaks or Auger peaks. And the difference between the photoelectron peaks and the Auger peaks is that photoelectron peaks are evidence that a hole is created in a core level, whereas an Auger peak is evidence that a hole is filled within a core level, and as a consequence of the Auger process, an electron is emitted that has an energy that is characteristic of the difference between the system before and after the hole is filled. The Auger process is not the only mechanism by which a hole in the K shell can be filled. In fact, the alternative mechanism is precisely the mechanism that is used in an X-ray gun to create X-rays. In the case of an X-ray gun, the mechanism by which X-rays are produced is that electrons are accelerated at high voltage towards a material such as aluminium, with a view to creating vacancies in the K shell of aluminium. And once these vacancies occur, so we have holes in the K shell, then relaxation occurs just as it did with Auger. In fact, both Auger and this process will occur. However, in this case, we're looking for X-rays, and the Auger electrons will be trapped by an aluminium window to prevent them from exiting from the X-ray gun. So we end up with X-rays of a characteristic energy that is defined by the relaxation between two states, either the L3 or the L2 relaxing into the K shell. And these are slightly offset by virtue of spin-orbit coupling in terms of energy, and so we end up with a doublet shape in addition to the distribution of energies that we would expect from X-rays from this type of relaxation process. The reason that I'm looking at a dual anode rather than a monochromated aluminium system is that the use of aluminium and magnesium anodes within a dual anode can sometimes produce an effect that helps to explain what we see in the magnesium oxide spectra in terms of ghost peaks. That when we have a dual anode, the idea is that if we switch on the filament for the aluminium, then all electrons leaving this filament will arrive at the aluminium. And when we switch on the magnesium filament, the same is true, that only electrons aimed at the magnesium will arrive at the magnesium, and there will be no crossover between the aluminium and the magnesium. However, historically, it has been possible to see dual anodes where we see a crossover effect, and that is to say that if we have the aluminium filament on, then rather than just hitting the aluminium, it's possible to see there's evidence that the magnesium is also being hit by these electrons, either directly or indirectly. There's some type of signal that is being generated from both anode materials, which means rather than having a single energy for the X-rays, we actually have two, one corresponding to the aluminium and one corresponding to the magnesium. And this produces spectra with some interesting properties, and I'll now show you an example of this. This is a spectrum from a silicon wafer with an oxide layer, and you can see that we've got an oxygen peak and silicon peaks. So if we bring up the element library and we look at the acquisition conditions of this spectrum, you can see that it's been acquired using an aluminium anode, and it's a dual anode, but nevertheless it's supposedly an aluminium anode. So if we indicate we've got a few elements here that represent the expected composition, which is silicon, oxygen and a bit of carbon, then we end up with a set of markers that are positioned in binding energy based on the aluminium anode. Now we see additional peaks. In particular, we see a peak here, and the difference between this oxygen peak and this peak here is about the difference in the energy between the X-ray energy for aluminium and magnesium. So let's do an experiment, and what we'll do is we'll change the anode from being aluminium to magnesium, and we'll specify the energy that we expect for a magnesium anode X-ray source. And when I press OK, you'll now see that all the peak markers have moved as if we've got a magnesium X-ray source. What we can see is that now the silicon is indicating we've got peaks here and here, and the oxygen has a peak here. So what we've got is crossover between the aluminium and the magnesium. We're not just measuring using a single X-ray source, we're actually measuring a spectrum with two X-ray sources active at the same time. So we get these ghost peaks. This is a result of crossover between the aluminium and the magnesium anodes in a dual anode X-ray source. So we can see for a dual anode it's certainly possible to see ghost peaks, but that doesn't explain what we see in this magnesium oxide data, because these data were acquired using a monochromated source. What do we mean by a monochromated source? Well, rather than a dual anode where you have an anode with magnesium and aluminium, so there's the potential for a problem, here we've just got aluminium, and it's arranged such that X-rays that are emitted from the aluminium are diffracted by a quartz crystal, so only a very narrow band of energy, photons, actually arrive at the sample. So even if we had magnesium on the anode, it would not produce any X-rays that ultimately got through to the sample. Up to this point in the video, the evidence of a ghost peak is rather tenuous in the sense that it really is quite a small peak in this survey spectrum. But to dispel any thoughts that this doesn't exist, a measurement has been performed where the interval over this ghost peak has been integrated for a longer period of time and repeated 3 times. And each time we can see there is genuinely a peak here. In fact, if we sum all of these data that include oxygen 1s, we can see the relative intensity of the ghost peak to the oxygen 1s, and you can certainly see that a peak does exist, but indeed it is really quite small when compared in counts per second between the oxygen 1s from magnesium oxide and this ghost peak. If we measure the distance in energy of the oxygen 1s peak to this ghost peak, we see that it's about 233 electron volts. And this is the difference between an X-ray energy from an aluminium anode and an X-ray energy from a magnesium anode. However, we have a monochromatic X-ray source, so we know there can't be X-rays that are generated from the anode. So the explanation that is given for this ghost peak is that this ghost peak is a result of X-rays that are being generated within the sample itself. And this is explained very nicely by Mark Biesinger on his website, xpsfitting.com.